in the home stretch for chapter 6. So here's a question. How many kilograms of liquid octane of CH18 must be combusted to produce 1.0 times 10 to the kilojoules of energy? It looks like a very bare bones problem, but it's actually kind of a lot to it. All right, so how do we do this? Any ideas? Right, write the combustion reaction. So, strategy-wise, we have to write out the combustion reaction, figure out what delta H is of that reaction using heats of formation, and then use the delta H to figure out the rest of it. So just like all chemistry problems, if there is chemistry going on, we have to start with the chemistry first. Okay. So what is the reaction of liquid octane combusting? Alright, so CH18. Check this for carbon. We don't have octane in this table. All right. Let me just look for liquid octane. So look up formation of octane. There we go. Negative 249.95 kilojoules per mole. I seem to have lost my notes for this problem, so we'll just run with this. All right, so heat of formation for liquid octane. So it's negative 249.95 kilojoules per mole. Okay. So octane reacts with what? O2, and we get right, CO2 and water. What is delta H about? Right. So we got to balance it. C8, we have 8 carbons. We have 9 oxygen, 18 hydrogens. 16 plus 9 is 25 oxygens. So we have 25 there or well, 25 halves. We could leave the half in there if we want, but we don't like fractions generally. So I'm going to go ahead and get rid of that. 2, and multiply that by 2, and these by 2. Okay, so we have a balanced reaction. Let's calculate the enthalpy. So delta H is equal to, we've got 16 times negative 393.5 kilojoules for CO2 plus 18 negative 241.8 for water. Whoops. Okay, all of that minus 2 times the negative 249 for the octane, and then 25 times 0 for the oxygen. So we get, for that whole thing, we get 16 times negative 393.5 plus 18 times negative 241.8 for water. So you should get, let's see, negative 10,648.8 kilojoules for the product side, and then for the reactants it's 2 times negative 249.95. So this turns out this is negative, so we're going to add that. All right, and then so negative 10,648.4 plus 499.9. So you would get a negative 10,148.5 kilojoules. Is this the answer? No, it's not the answer. We still have more to do. All right. So this is delta H. Delta H reaction. But what it's asking us for is how much kilograms of liquid octane do we need to get 1 to the 11th kilojoules of energy? Any ideas on what to do? No, not really. All right, so you might remember this from Chem 107, but in Chem 107, you would typically be given a reaction, it'd be given a delta H. You need to look at the energy to mole ratio. So delta H, negative 10,148.5, and this is per 2 moles of liquid octane. Does this ring a bell at all? Maybe, maybe not. We did one of these last time too, but so that means that in order to get 1.0 times 10 to the 11th kilojoules of energy. We need to somehow cancel out the kilojoules and get to moles, and then get from moles to grams, and then get from grams, of course, to kilograms. We know that there's 1,000 grams in 1 kilogram. We know that, right? What numbers can we put here, mole to kilojoules? Well, this is it. So we can say, okay, negative 1,148.5 kilojoules for every 2 moles of C8H18. And then the molar mass of octane is what? Because you memorized all these molar masses, right? After all this time. So you have 8 times 12.01 plus 18 times 1.01. So you get 114.26 grams per mole per. Now, how many moles do we put down here? What does the molar mass always give you in terms of how many moles? It's always just 1, right? So for every 1 mole of the octane, you have that many grams. So you can see now how we can figure out how many kilograms to give us this much energy. So running this through now, okay, divided by 1,000 times 2 times 1e to the 11th divided by 10,148. So this is quite a bit of energy. All right, so the answer would be 2. Sticking with significant figures, of course, 2.3 times 10 to the 6th kilograms of fuel, of C8H18. All right. Yes?
Can you explain the 0 kilojoules?
Can I explain the 0 kilojoules here? So this is for, this is 2 times the octane and 25 times the oxygen. Oxygen is the standard element. It has 0 from the table. All right, so if you looked at the heat of formation for oxygen, it'd be 0. That's where that came from. Keep coming with the questions.
So the answer can't be negatives?
Right, okay, so here's, that's a good question I was hoping you'd ask. Okay, so here's the thing. The enthalpy of reaction for the combustion of octane is this negative number, right? It's an exothermic reaction, it releases heat. Now here's the thing, if you're producing 1.0 to the 11th, that's also going to be negative because it's being released from the reaction. So it turns out that there's an unsaid negative here, which cancels out the negative here. Yeah. I mean, it's kind of like saying, well, how much kilograms do you need to produce this much energy? Would you tell me, yeah, I need negative 2.3 times 10 to the 6 kilograms. That's like saying, yeah, I paid a negative $5 for this, whatever it is you bought, right? So when we talk about mass needed, it's always going to be a positive number. If it asks you for how much energy was required, you would still give me a positive number. If it asks you for what was the change in energy, now you got to have a negative or positive. All right, that matters. So when it asks you for a change in something, then there's a sign that needs to be there. Okay. So that's quite a bit of fuel, right? 2.3 to 10 to the times 10 to the 6 kilograms. It's a lot of weight of octane fuel, right? But this is a lot of energy too. So from Chem 107, this bottom part that I have here in blue, this is probably something you saw in Chem 107. Now we're tacking on this kind of calculation onto it to where now you have to figure out from heats of formation what delta H was, and then you can use it in this problem. So welcome to Chem 111A. It's like the, you know, it's just a layer under this. So hopefully you recognize at least the bottom calculation from last semester or whenever you took Chem 107. Hopefully that looks familiar to you. Okay, now it's tacking on this enthalpy of reaction calculation onto that. Okay. Sometimes you can maybe even have a calorimetry problem tacked onto this. Okay, maybe you figure out what delta H was from a calorimetry problem, and then you can use it for the rest of this. You know. All right. Here's one more problem. This is actually in your problem solving packet. So it's very similar. What I propose is we can just save this for problem solving. It's in your packet. How much time do we have left? Yeah, 5 minutes.